Hello again everyone, welcome to Setco College online classes. In this video today we're going to discuss the grade 12 topic, the very first topic, which is momentum, its conservation, and other related topics. Okay, so without wasting much of your time, as you can see in front of me, I've got the ATP, or what you're supposed to follow throughout the year. So I'm going to zoom in so that you can see what is there. Okay, so in this topic we're going to talk about momentum, which simply means defining it, and you have some few calculations on it. Then we have some few vector diagrams, because momentum is a vector quantity. Then we can see how we relate that to Newton's second law of motion. Then we're going to talk about impulse, the principle of conservation of momentum, elastic and inelastic collisions. Then we'll talk about some explosions, couples, and independent variables. Okay, I'm going to drop the video, the link in the video description below, so that you can download the annual teaching plan. In fact, I'm going to drop the link for all the ATPs for the entire year, so you can follow it, or you can click the link in the video description below. Then it will take you straight to the ATPs. Then you can see what you're supposed to cover throughout the year. Okay, so without wasting much of your time, let's define momentum. So this topic, we're going to discuss momentum. We are talking about momentum. Okay, so what is momentum? What are we talking about when we talk about momentum? Remember, when let's say a car is moving, you are inside the car is mass. It will also move at a certain velocity, but before it starts moving, it will be stationary until the driver puts in the key, ignition, then the car starts moving. Initially it's at rest, it's not moving, then it starts moving at a certain speed. It has a mass, so it allows us to calculate the momentum of that particular car. So how do we then define momentum? It's simple, because the car has mass and it also has a velocity, whether it's stationary, not moving, which means pretty much the same thing. So momentum is basically the product. So when you define momentum, is the product, let me zoom in that out a little bit. Okay, so the product of mass is the product of mass and velocity, product of mass and velocity of an object. That can be any object, any object. So the product of mass and velocity of an object. Okay, so it can be an object. So in physics, remember, these objects, we normally refer to them as bodies. Okay, so that's the very first thing we need to know. So is the product of mass and velocity. But as we know that velocity is a vector quantity. Velocity is a vector quantity, and from previous knowledge, which is grade 10 and 11, you know that if you multiply a vector times a vector, it will give you a vector. A vector times a scalar, it will also give you a vector. Okay, so we know mass is a scalar quantity, so mass is a scalar. Mass is scalar quantity and velocity a vector quantity, so it fits which description? Vector times scalar, so it will give us a vector quantity. Okay, then without wasting much of your time, let's have some examples. Let's just assume that we've got a car that is moving due east. Remember, we are saying it's a vector quantity, so we are saying momentum, which is represented by small letter p, is given by mass times velocity of an object, which means mass is measured in kgs and velocity is measured in meters per second. But since we're calculating momentum, this velocity must have a direction. It must have a direction, which means momentum has a direction. So let's just assume that a certain car is moving at 20 kilometers per hour g east. So let's assume that this car has got a mass of 1,200 kgs. So it's 1,200 kgs. So we can calculate the momentum of this car P is equal to mv. Okay, mass of the object 1200 kgs times the velocity is given as 20 kilometers per hour. Okay, so if it's 20 kilometers per hour, it's difficult for us to go into work. If you look at it here, this is not in SI units, but yeah, we're dealing with physics, so we must change 20 kilometers per hour into meters per second because we are dealing with SI units. Okay, so how do we then change from 20 kilometers per hour to minutes? Okay, it's simple. We know that 1000 meters is equal to 1 kilometer. So we can change, in this case we've got 20 kilometers, 20 kilometers, which is simply 20 k's. So what we are looking for x meters. So what does that mean? X over 1000 is equal to 20 over 1, because that's 1 there. So that will give us, in other words, we're simply going to multiply both sides by, so you multiply here with 1000, multiply there with 1000. So here I'm just trying to show you how to do this without a calculator. So if you say 1000 times 20, it will give you 20,000 meters. So this is 20,000 meters. But we also know that 1 hour is 3,600 seconds. So an hour, 1 hour is equal to 3,600 seconds. Okay, so now we can find our velocity in meters per second is 20,000 divided by 3,600. Okay, so if you do that way, we should be getting, let me do it on the side. So it's 20,000, 20k divided by 3,600. So if you've done the calculation right, you should be getting 5.5555. So I'm going to round it to decimal places, 5,5. Let me round it to 3 decimal places, 5,56. Okay, meters per second. So now in my calculation, I'm just going to come here, then I'll say this is 1,200 kgs times 5,556. Okay, then I'll get a certain answer there. But remember, now this is kgs and this is meters per second. So our answer we get there is supposed to be kg, whatever the value is, kg meters per seconds. Or more precisely, if you want to do your work precisely, you could have just come from here, then you say, okay, this is 1,200 kgs. I'm multiplying with what? With 20,000 meters on, what do we have there? It's 3,600 seconds. Okay, so at the end of the day, you end up having whatever the value there is still in kg meters per second. Kg meters per second. So it will still be the same thing there. Okay, and it's more precise. Anyway, let's move on. Since we said this is a vector quantity, we also know that it has direction. Let's just assume that if there's a tennis ball moving at a certain speed going to the left. So this is a tennis ball. Let's assume that is having a momentum of x kg meters per second. There's a tennis ball moving there. Then it's going to hit a wall. Let's say it's going to hit a wall. Then when it reaches the wall, it's going to come back at a certain momentum. Let's say it's y kg meters. Let me zoom in. So y kg meters per second. Okay, so when it's now coming back, there's something you need to know. The tennis ball is going to be in contact with the wall for a fraction of a second. So for a particular amount of time, the tennis ball is going to hit there. So there's going to be energy that is going to be wasted due to heat. Okay, so energy will definitely going to be dissipated, so it's going to reduce. So when the ball is going to come back, its velocity will reduce. So when the velocity reduces, it also means that momentum is going to reduce, because we know that P is equal to mv, and these two, they are directly proportional to each other. So the moment the velocity reduces, momentum will decrease. Okay, so if momentum decreases, it means also velocity is decreasing. So let's just assume that now, if we're going to find change in momentum, remember, change simply means momentum final minus momentum initial. Okay, so in this case, the change in momentum is y, which is the final momentum that we're going to have, y minus the momentum in this direction, which is x, going in the other direction. So end up having this, whatever this value is, will be in kg meters per second. So kg meters per second. Okay, so that's the change in momentum. So why do you now calculate this change in momentum? It also helps us to visualize things or draw vector diagrams. So let's just assume that this x is equal to 5 in this case, and y is equal to 2. If I'm to calculate my change in momentum, it's going to give me 5 kg meters per second minus 2 kg meters per second, which is equal to 3 kg meters per second. But in this case, am I right if I'm going to say it's 5 minus 2? Because we're saying this is going to change, but this is initial and this is final. So in this case, I'll be wrong. So to do the right thing simply means you have to say change in momentum, in this case, is equal to final, which is 2, minus initial, which is 5. Then we're going to have up having minus 3 kg meters per second. This minus simply means that we are now moving in the opposite direction. So if assume this was going to the right, this simply means now we are going to the left. So this simply means I can rewrite this answer as simply 3 kg meters per second left. Look what we have in this answer. We have got the magnitude, which is the size, and we also have the direction. Why are we having both magnitude and direction? Because momentum is a vector quantity. Momentum is a vector quantity. So in simpler terms, this is if I'm to ask you to illustrate this answer as a vector diagram. Remember, I had 5 kg meters per second there, going in this direction, and I had what? I had 2, so the arrow for 5 kg meters per second has to be longer than that of a 2, so 2 kg meters per second. Okay, so if I'm going to have a resultant of this, it's there, which is what? 3 kg meters per second. Okay, so this is the resultant. Not here. We are moving in this direction. Okay, then there's a force as we hit here in this direction, as we're going to hit the wall. There's a force that we're going to exert on the wall, and the wall is also going to exert the force, another force on the ball, which is action and reaction, Newton's third law of motion. Remember, if a body A exerts a force on body B, the body B also exerts a force on body A, which is exactly the same in magnitude and only acts in the opposite direction. So here, 2 kg meters per second in this direction. Okay, so it means the resultant should be, if this one is acting in this direction, so this one should be in that direction. So the resultant in this case is that one. Okay, but this is our resultant momentum in this direction. Okay, thank you. Let's move on. Momentum on its own, unfortunately, we don't get questions that are this easy, where we just have to illustrate and draw these diagrams. No, it's not always like that. So you notice that most of the times we have proper questions. So this type of questions, they come in form of conservation of linear momentum and impulse. So conservation of linear momentum and impulse, they are also linked by Newton's second law of motion. Let's move a little bit back and see how this come about. Remember in grade 10 and 11, you were taught that V, which is the speed, is simply a distance on time, isn't it? Rate of change of displacement with time. Okay, so here V is equal to d over t, and we also taught that A is equal to change in velocity on time, isn't it? V delta V on delta t. Okay, so acceleration is the rate of change of velocity. Acceleration, the rate of change of velocity. So when you say rate, it means there's an element of time. Okay, so let's rewrite this in terms of formula. So acceleration is equal to V final. Change means there's a final and initial. V final minus V initial on delta t. Delta t, you can leave it as delta t, but we also know that it's change in time, which is tf and minus ti. Okay, then let's have Newton's second law of motion. Newton's second law of motion is given as F net is equal to ma. But already we have calculated A there. We know that A is given by that. So we can rewrite this as M times Vf minus Vi on delta t. I can rewrite this, or I can simplify this just by clearing the bracket, and it will give me mv final and mv initial, everything on delta t. But if you look closely there, we said momentum is equal to mv. What we have there is mvf, which is simply final and initial, but this is mv and this is mv. So I can rewrite this as delta p on delta t, or I can rewrite this as initial, this, which is the same thing as initial momentum minus final momentum on delta t. Okay, so F net can be found as F net is equal to that. Now, what happens if I decide to multiply both sides with t? Delta t, I now have F net delta t is equal to change in momentum. This is what we call impulse. We call this impulse. Impulse. So this simply means, if I'm to ask you to define impulse, impulse is the same thing as saying impulse is given by the product of mass, the product of the net force and contact time. Why am I saying contact time? Remember, like when the situation I gave you with the tennis ball is going to spend a fraction of a second in contact with the wall. So that's the contact time that we mean. Normally when you're dealing with impulse, there has to be contact time, or the time that two bodies are going to be touching each other. Okay, or I can define this also in terms of momentum. Remember I was saying F net delta t, which is impulse, is the same as change in momentum, which means I can also simply define this as impulse is equal to change in momentum. Okay, what does this tell us? It simply means there are two ways in which we can calculate impulse. So I can say impulse, when I'm calculating impulse, I can say this is F net delta t, or I can simply say momentum final minus momentum initial, they will both give me impulse. So how do I know which formula am I going to use here? Okay, if you have got a situation where you are not given the contact time, you definitely have to use this. But if you have a situation where you are given the contact time, you definitely have to use the contact time. So you check what you are given and you make relevance of it. There's no way they'll give you contact time and then you don't have to use it. So if they give you contact time, you must use it. Okay, you can pause the video at this moment and try and let all this sink in. Another thing that we're going to make use a lot in this topic is the principle of conservation of momentum. So the principle of conservation of linear momentum simply says, in an isolated system, I'll write this down for you so that you remember. Let me zoom in. Okay, so in an isolated system, principle of conservation of linear momentum simply states that in an isolated system, the total, let's mark a little bit. Okay, so in an isolated system, the total linear momentum is conserved. So the total linear momentum is conserved there. What does that mean? Why do we have isolated system and linear momentum in the definition? So by isolated system, we simply mean there's an absence of external forces. There's no other forces acting on the system. So here, isolated system simply means no external forces are acting on the object or on the system. No external forces. This is very, very important. So you notice that some of the questions, they can ask you that, let's say in a question, they will ask you to define isolated system. What does the term isolated system mean? You simply go and say, this means that there is no external forces acting on a system or on an object. Okay, linear momentum, this simply means the momentum we are talking about is in a straight line. The momentum we are talking about linear from the word line, so we are talking about linear momentum, which is momentum in a straight line. So for grade 12, we normally deal with the motion that we deal with is in 1D, one-dimensional motion, and we normally use it in a straight line to avoid complications. But in real life situations, you notice that it's not always the case that we've got a linear momentum. But in grade 12, we stop at linear momentum. Okay, moving on. We now know that isolated system simply means there's no external forces, and in that case, momentum is conserved and it's acting in a straight line. We're also going to talk about, let me just give you all the theory of this topic before I start talking about the calculations, before we start putting calculations in place. Okay, so we are also going to talk about elastic and inelastic collisions. So remember, since we're talking about momentum, we are going to talk about collisions. There has to be collisions. Okay, so these collisions can either be elastic or inelastic. So collisions can be elastic or inelastic. So in an elastic collision, kinetic energy is conserved. Kinetic energy is conserved. By conserved, you simply mean the kinetic energy before the collision occurs is exactly the same as the kinetic energy after the collision has occurred. Okay, the same thing occurs with inelastic collisions. So in elastic collisions, these ones, kinetic energy is not conserved. So kinetic energy, EK, not conserved. So in these ones, we are not conserving energy here. Kinetic energy is not conserved. Okay, so things to note when we're dealing with the principle of conservation of linear momentum. Remember, we are saying conserving, which simply means whatever is happening before is also happening after. And we are also talking about these collisions being elastic and inelastic, and we are also talking about conservation of energy there. Okay, so To simplify this, when we're dealing with the conservation of linear momentum, remember we are simply saying the moment summation, adding all the momentum that has occurred before the collision, it must be exactly equal to the momentum right before, which is I, and after, which is final. Okay, so momentum before the collision, this is I, is exactly the same as momentum after the collision, which is F. Okay, so what does that mean? We know that let's just assume that we've got multiple bodies, so I can have more momentum and velocity, mass and times velocity of, say, object 1 plus that of object 2. So this is initial, then maybe we've got plus other bodies up to n bodies is the same thing as saying momentum of objects after the collision, which is the m1v1, but now this is final velocity, plus m2v2 final velocity, plus whatever number of bodies that we have there, which is n. Okay, but in grade 12, the reason why I put 2 first is that in grade 12 you normally do 2 bodies, you never do 3 bodies. Okay, so whenever this collisions occurs, let's just say this is a car hitting another car and they move independently after the collision. There's a situation where the kinetic energy can be conserved and kinetic energy cannot be conserved, of which in terms of let's say 2 cars are hitting each other, head-on collision, there's no way kinetic energy is going to be conserved, because there's going to be sound and there's going to be heat. So some of the energy is going to be lost through heat, some of it is going to be lost through sound. Okay, so kinetic energy is not conserved. Okay, so if kinetic energy is not conserved, how do you see that? The speed at which these cars were moving with before the collision and the speed they will move at after the collision would definitely be different. In other words, they're going to decrease. What is causing the decrement is simply because sound is going to be made. Heat also is going to be made due to friction when they are hitting each other and stuff. So we're going to lose energy due to friction, we're going to lose energy due to sound, and when they are hitting each other, there's going to be heat made there. So there's a whole lot of energy that is going to be lost. So kinetic energy is not going to be conserved. Otherwise, if the kinetic energy is conserved, these objects before collision and after collision, they will move at the same speed, which is nearly impossible. Okay. Now, let's try and see how do we use all these things in calculations. But before we start with these calculations, there are some things that I need you to understand. And these things are, when we're dealing with these calculations, you notice that we're going to start with the bodies. Some of these bodies will start as one. So we might have body 1, and body 2 joined together and before the collision. Then after the collision, you notice that these 2 bodies will then separate, and when they are now moving, body 1 will go in that direction and maybe body 2 will go in that direction. They have separated. So initially they were 2 joined together, so we call that a couple. So a couple, then when we're dealing with our calculations, you see these 2, they are joined together, so it means the masses are combined. So we normally say m1 plus m2. They are moving at the same speed because they are combined together, so they normally have the same initial velocity. Then after collisions, that's when they're going to have m1 moving with its own speed, v1, which is now its final speed, and m2 will move with its own velocity, which becomes final. Now look, initially the masses were combined and they were moving at the same speed or same velocity. Now they've got different velocities and their masses are now separated. This is because a couple, when they join together and they separate. So with couples, they start as one thing, then they separate. Okay, then we also have an explosion. We also have an explosion. Okay. I made a mistake. Let's pause that.